Hello, I'm Robert Pigg, and welcome to my lab report. The goal of Lab 2 was to video a falling object, or in other words, an object experiencing gravitational acceleration and air resistance. In my experiment in particular, the air resistance was quite high, allowing me to have unique results and come to interesting conclusions. After videoing, I needed to use Tracker to obtain position time data. Using this data, I was tasked to create two computational models using Newton's second law as the backbone. One only needed to model the effect of gravity on the object, and the other needed to model the effect of gravity and the effect of air resistance. Modeling the air resistance was hard because I had to find the mass of my object and the B value, and the B value is the coefficient of the force of drag. Finding the mass was hard because my object was of an unknown weight, and finding the B value was hard because the air resistance was quite strong and hard to get precisely. Then, using these models and the observations from Tracker, I needed to make a graph comparing the three sets of data. From this graph, we will be able to come to important conclusions about the effects of gravity and air resistance on an object, as well as demonstrate the use of computers and programming for determining important physical quantities. The structure of the rest of this lab report is going to go like this. Next, I will talk about my observations in Tracker, and then the process of creating my models and the code behind them. From there, I will compare my models and my observations, and then lastly, some final thoughts and conclusions. In Tracker, I inserted the video and went frame by frame to select the position of my object, which was a plastic bag attached to a bookmark. I put a blue post-it note on the bookmark to give it contrast against the background, allowing me to be more precise, thereby reducing the human error present in the process of selecting the position. Some other possible sources of error are that the time span is short, so I have less data to compare, and the possible tilt of the camera, which would disrupt the scaling, which I calibrated using the height of one brick. To create the models, I used fundamental physics principles and the observations from Tracker. The initial conditions were the same for both models. Because the origin in Tracker was placed on the object, the initial position is 0. Using the first two sets of position time data, I found the initial velocity to be negative 1.39 meters per second. Similarly, the models use the same assumption that the system is the plastic bag and bookmark, while the surroundings is the Earth. They also assume the two primary forces are the force of gravity and the force caused by air resistance. The models also use the same loop, which repeatedly applies Newton's second law in the form of F equals ma to update the position and velocity repeatedly to create the graph. The models differ in what F net is. For the model without drag force, the F net is the force of gravity. For the other model, F net is the upward force of air resistance subtracted by the force of gravity. To approximate B, the coefficient of drag, I had to guess and check repeatedly until the final position of the model and the observation were the same. The model on the top left is the model with drag force included, and the one on the right is the one only with gravity. As you can see, the model on the left goes less far and has less downward curve, meaning less acceleration. This makes sense because the drag force slows down the object. If I change the graph of the model with drag to be a velocity time graph, we can see the effect of drag. Because drag increases exponentially as velocity increases, the object accelerates due to gravity, but slowly levels off. This maximum velocity due to drag force is called terminal velocity. The model without gravity does not have a terminal velocity because no force counteracts gravity, so it will keep accelerating downwards forever. On the last slide, we analyzed how an object will accelerate downwards until it hits terminal velocity. However, what would happen if the object was thrown downward faster than the terminal velocity? By setting the initial velocity to negative 2.5 meters per second in the model with drag, which is bigger than the velocity where it leveled off on the last slide, we can see that the velocity decreases due to the effect of drag until the same level as before. This means no matter the initial velocity of the object, the terminal velocity is the same, so it will accelerate or decelerate until that velocity. We can see this in the net force formula, where the force of drag increases exponentially as velocity increases. So there will be a sweet spot where the forces of gravity and the forces of drag counteract each other, leaving you with constant velocity. Remember that this is a velocity time graph and not a position time graph. The velocity does increase, but it is still negative, so the object is still falling downwards. And now to compare the models. The model without drag is not similar whatsoever to the observed line, because it lacks the upward force of drag, meaning the F net is stronger downwards, resulting in a faster downward acceleration. However, the model with drag is similar and models well the actual data. However, it overestimates position at every level until the end, possibly due to a miscalculation of the initial velocity and/or position. leading to the b value being slightly higher than actual in order to bring the two lines together. In the future, I will need to compare all points to see if my model is accurate, and not just the last ones. This lab is important because it demonstrates how terminal velocity works, as well as shows how quickly it can come into effect. Similarly, this lab shows the power of computational models because if correctly used, they can find values such as the b value. Finding these values scientifically can be difficult, so computational models present an alternative way to determine them.